So this is section 2.4, which is on the Cauchy-Riemann equations. So what the Cauchy-Riemann equations are going to allow us to do, they're going to allow us to be able to determine whether a function f is differentiable at a point. Okay. So to derive these Cauchy-Riemann equations, we're going to actually consider a function f that has a real part, which is u, and an imaginary part, which is v. And then we're going to suppose that f is differentiable. And then from that, we're going to derive equations based on the fact that if f is differentiable, okay, then this limit exists. And so, of course, this is the limit definition of the derivative. Okay, and since this limit exists, it exists regardless of our path towards z. Remember, for complex functions, we have to consider all paths that approach z in the complex plane. Okay, and we're going to choose two specific paths, one being a horizontal path and another being a vertical path. And from that, we're going to be able to derive the Cauchy-Riemann equations. Okay, so the first path we're going to take is horizontal. So if we're going to approach so we're going to approach z along the real axis, or it's more correctly, we're approaching along a line that's parallel to the real axis. In any case, when we do that, we basically set delta y equal to 0, the delta y that's part of the delta z. Okay? So when we do that, this limit becomes, we have a limit as delta x goes to 0 of f of x plus iy plus delta x, okay? And then minus f of x plus iy. That's in the numerator, and this is all divided by delta x. Okay? And so now we basically substitute in u and v. So we have, in the next line, limit as delta x goes to 0, u of x plus delta x, y, plus I times v of x plus delta x, y, and then minus, in parentheses, u of xy plus I v of xy. Okay. And this is all divided by delta x. Okay. And so what we're going to do is we're going to split this up into real part and imaginary part. So our next line is we're taking limit as delta x goes to 0 of u of x plus delta xy minus u of xy. Okay? And this is all over delta x. Okay? And then plus, and I'm going to separate this into two limits. So this will be I times a limit as delta x goes to 0 of v of x plus delta x y minus v of x y. And this is all divided by delta x. Okay? So I'll give you a moment to think about what these limits are. Okay, so if we look at the left-hand side, we have u of x plus delta x y minus u of xy divided by delta x. Okay, so if you go back to Calc 3, this should look familiar to you. Okay, this is basically a first partial derivative of u with respect to x. Okay, so this equals, this first limit is du dx. And the second limit, well, that's dv dx. So we have that this limit, okay, we approached along a horizontal axis, okay, and this is f prime of z. So this is an expression for f prime of z, okay. And what we're going to do next is derive another expression for f prime of z that must equal this. Okay, and then from there we'll get the Cauchy-Riemann equations. So this was approaching along the real axis. Now let's change that to approach along the imaginary axis. So I'll change this part here, and I'll erase all of this as well. So now we're going to approach along the imaginary axis. Again, it's really parallel to the imaginary axis, and that means we're going to set delta x equals 0. Okay. So now the limit that we look at is the limit as delta y goes to 0 of f of x plus I y plus delta y, okay, and then minus f of x plus iy, okay. This is all divided by delta y. And now if we substitute u and v in for f, this is a limit as delta y goes to 0, and the denominator here should have an I delta y. So the next line is, so u of x y plus delta y and plus I v of x y plus delta y. Okay. And now minus, in parentheses, u of xy plus I v of xy. This is all divided by I delta y. And we do the same as we did previously. We split this up into real part, imaginary part. And so that leads to the limit as delta y goes to 0 of u of x y plus delta y minus u of x y. This is all divided by I delta y. And that's one limit. And then plus a limit as delta y goes to 0 of, so let's see, the i's, there's going to be a canceling of I, so we have a v of x y plus delta y minus v of x y. Okay. That's all divided by delta y. All right. So these limits, again, they should look familiar. All right. So here, this limit on the left, this is looks like du dy. Okay. But we also have to be careful. There's an I here in the denominator. Okay. And so to take care of that I in the denominator, we multiply top and bottom by I. And so that's going to lead to a factor of minus I, right, in the numerator. So this limit here on the left is minus I du dy, right? And this limit over here, this is simply dv dy. And since our function is differentiable, this is another expression for f prime of z. Okay, and so if you recall our expression for f prime of z from previous part, so this is part 2. From the previous part, we had that f prime was equal to du dx plus I dv dx. Okay, and if we simply equate real part from on the left side to the right side, we have one of the Cauchy-Riemann equations. And then if we match the imaginary parts, we have the other equation. So those equations are, you can see here, du dx equals dv dy, and dv dx equals minus du dy. Okay? So those are Cauchy-Riemann equations. So we have du dx equal to dv dy. This is 1. And the other equation, dv dx equal to minus du dy. Okay? So from this derivation, let's now write down our theorem. Okay, so basically what we've shown is that these equations, the Cauchy-Riemann equations, must hold if f is differentiable. Okay, and so from what I just stated, we can write down theorem 4. And so theorem 4 gives us a necessary condition for a function to be differentiable. Okay, so a necessary condition for function f to be differentiable and I guess, I did this for an arbitrary value of z, okay, but if we look at a specific fixed point z sub 0, we want the Cauchy-Riemann equations to hold at z sub 0. So the necessary condition is that so for necessary condition for f of z to be differentiable at z sub 0 is that the Cauchy-Riemann equations must be satisfied at z sub 0. Okay, and so in the next video we'll actually look at some examples where we use the Cauchy-Riemann equations.